Many experiments appear to show that the quantum world is weird, but with a new approach to the mathematics of the Schrodinger wave packet, all this is changed. Experiments that previously appeared to show that time can go backwards in the quantum world no longer say that. Experiments that used to say, or appear to say, that a particle can be in two places at the same time no longer say that. Because of an expanded new approach to the mathematics of the Schrodinger wave packet, the quantum world is transformed so that it makes sense, so that it's like the classical world of everyday experience. Weirdness is gone. This is a picture of a Schrodinger wave packet, which is the linchpin of quantum mathematics. And quantum mathematics is the most powerful science that humans have ever had. This wave packet is a sinusoidal wave moving to the right, but it's made up of a line, and in which direction is the line itself moving? You probably assume that it's stationary, but in my model, the line itself is moving rapidly at light speed to the left. Think of it being like a river flowing rapidly to the left, while on the surface of the river are waves going in the opposite direction. The wave packet represents a particle. Our view of the Schrodinger wave packet is identical to that of quantum mechanics, but we are including a larger context that no one else knows about, which is that our wave packet is part of an elementary wave which is traveling in the opposite direction. It is well known in quantum mechanics that waves can travel in opposite directions simultaneously. For example, a plane wave coming in from the right, striking an infinite barrier, doubles back on itself and is traveling in both directions simultaneously. This diagram shows a particle source or gun on the left, and on the right a detector. At this point, no particles are being emitted. There is a line connecting them. This line represents an elementary wave coming from the detector to the particle source. The line is inviting a photon to come strike the detector. The world is more interconnected than we realized. It turns out in our theory that no particle can strike a detector without being invited. Now this line represents a zero energy wave going from the detector to the gun, and many people erroneously believe that there can be no such thing as a zero energy wave. That is naive. The Schrodinger wave itself is a zero energy wave. The Schrodinger wave carries probability amplitudes, but not energy. And so we're simply extending the idea of a zero energy Schrodinger wave to include an elementary wave going in the opposite direction. So according to our model, which is called the theory of elementary waves, TEW, there's an elementary wave going from the detector over to the particle source or gun. It's carrying no particles, and there are no Schrodinger waves anywhere to be seen. So after a while, a photon or particle emerges inside the gun, about to be fired. That particle has an effect on the incident elementary wave, namely it triggers that elementary wave to produce a wave packet to carry the particle in the opposite direction to the detector. So this means that not only can no particles strike a detector without being invited, but in addition, by the time the particle has left the gun, it already has a trajectory, namely the elementary wave going in the opposite direction. Now you may say, look, this is supposed to be mathematics. Where are the equations? Well, the equations don't fit so well into an 18-minute video, so I have published them in a peer-reviewed scholarly mathematics journal, which you can look up anytime free of charge. Now consider an experiment in which it appears that data can be erased backwards in time in the quantum world. This certainly is quantum weirdness if it's true. This is a famous experiment published by Yoon-Ho Kim et al., and it's called the quantum eraser experiment. Photons come from a laser over here. They go through a double slit barrier, and then behind the double slit barrier is something called a BBO crystal, which divides each photon into 2 photons. So you end up with 4 photons, 2 of which represent the going through the upper slit and 2 of which through the lower slit. Photons 1 and 2 go up here to the target screen where they inscribe an interference fringe pattern, a wave pattern. Now my diagram is much simpler than the one published by the researchers because I'm simply trying to teach you how to think about this thing. Photon 4 goes down to a beam splitter which randomly assigns it either to detector D3, which does know, or to detector D2, which does not know which slit was used. So in the final data set, it turns out that if you don't know which slit was used, then the interference fringe pattern on the target screen is still visible. But if you do know which slit was used after the fact, then the information on the target screen is erased, apparently backwards in time. This causes a lot of people to have migraine headaches because it seems pretty clear from the ordinary assumptions that data can be erased in the quantum world backwards in time, which certainly is quantum weirdness if it's true. However, when we look at this experiment as published, we find that it is grossly inadequate. It considers only photons and Schrodinger wave packets going from the laser to the detectors, and it leaves out the elementary waves, which is where the entire thing is decided. We start with the elementary waves starting at the detectors and going backwards through the equipment, backwards through the BBO crystal, backwards through the double slit barrier, and impinging on the laser. All wave interference is located at the laser. All decisions in this experiment are made by the photon before it leaves the laser. So this target screen that we're all so familiar with, what does it mean? Well, if it has a wave pattern on the target screen, that means that there is wave interference at the laser. If there is no wave pattern on the target screen, that means there is no wave interference at the laser. So how could that be? Well, if at the laser you have elementary waves coming through both slits, those 2 waves through the bottom and top slit will interfere with each other, and you will get an interference fringe pattern on the target screen. If, on the other hand, you have no elementary wave coming through the top slit and only an elementary wave coming through the bottom slit, there can be no interference with only one wave, and therefore the target screen will show no wave interference. There are 2 kinds of elementary waves impinging on the laser, and the photon has to choose which one. It makes that choice at random. On the one hand, there's an elementary wave coming from the target screen and from a detector that does not know which slit the photon came through. And it turns out that when you trace that backwards, the elementary waves impinging on the laser will be using both slits, and therefore there will be wave interference in the final data set. The other possibility for the photon to choose is an elementary wave coming from the target screen and from detector D3. Detector D3 can see the lower slit, but it can't see the upper slit because of the way the equipment is constructed. Now I've color-coded these waves so that anything connected to the lower slit is color-coded blue and anything connected to the upper slit is red. So when the BBO crystal tries to manufacture an elementary wave to go through the lower slit, it can do so because it has the ingredients it needs, which is a blue wave from above and a blue wave from below. But When the BBO crystal tries to manufacture a red wave to go through the upper slit, it cannot do so because it's missing half of the ingredients. Namely, there's no red wave coming from detector D3. So therefore, there's no wave interference if detector D3 is involved, and therefore there is a blank target screen. So when the photon makes its random choice as to which elementary wave to select, that selection has an impact on that particular elementary wave, namely that it triggers from inside the wave the emergence of a Schrodinger wave packet which will carry the photon away from the detector. Now, the only part of this entire mechanism that is considered in the original publication is the Schrodinger wave packet part. And they mostly left the laser out of their drawings because they didn't consider it to be of any importance. When we look at the experiment from this angle, there is no backwards in time destruction of data. There's no quantum weirdness. Everything looks sensible and exactly what you would expect. Now, you might say, I like your idea of getting rid of quantum weirdness, but this idea of detectors sending zero energy waves in the wrong direction is totally weird. It does not correspond with my idea of nature. Well, there's a couple of things to be said. First, with TEW, we make our weird assumptions at the beginning. We say, yes, there are elementary waves with zero energy going in what you might consider to be the wrong direction, the direction opposite the particles. That's weird. But we pay our weirdness tax up front. Quantum mechanics, on the other hand, makes sensible starting assumptions and does not pay a weirdness tax and is therefore penalized by the taxing authority forever with a misperception that the quantum world is weird. I propose that it is better and more honest to pay your weirdness tax up front. And as far as what nature is really like, do you think you know what nature is really like? If the quantum experts knew for sure what nature is really like, then you would not find quantum mechanics experts saying, as they do, that there is a consensus that we don't understand the quantum world properly. When someone says that a particle can be in two places at the same time, what they're usually thinking about is the double slit experiment. Here is a double slit experiment as conceived by quantum mechanics. A wave particle is fired from the gun on the left. It spreads out as a cloud of probability amplitudes. Some of the cloud leaks through the two slits and moves to the right, and eventually, unpredictably, a dot appears somewhere, and that is called wave function collapse. So as you can see, a particle not only can be in two places at the same time, it can be spread out like a cloud all over the place. Einstein decisively proved that this model is wrong. Einstein said that whenever a dot appears anywhere, the entire cloud everywhere must vanish faster than the speed of light. If the entire cloud did not vanish, some other part of the cloud could produce a second dot, which would be impossible since only one particle left the gun. No one has ever come up with any explanation of how the entire cloud of probability amplitudes would vanish everywhere instantaneously faster than the speed of light, and therefore Einstein has proved one thing about what you've just seen on your screen, which is that it is wrong. It can't be that way. We've got to find some other model. According to TEW, every point alpha on the target screen emits elementary waves which move toward the double slit barrier. The top of this diagram shows the Thomas Young model, in which wave interference is to the right of the barrier, and the bottom picture shows the TEW model, in which wave interference is located to the left. The waves from point alpha impinge on the two slits, slit A and B, and as they refract through those slits, they have a phase difference, theta. Theta is determined by where on the target screen point alpha is located. The waves then converge and impinge on the particle gun, continuing to have the same phase difference, theta, and theta determines whether the wave interference at the gun is constructive, intermediate, or destructive. For example, if the wave interference is destructive, that wave will have zero amplitude at the gun, and there's no probability that the electron will choose that wave to follow backwards, and therefore we know that in the final data set, point alpha will remain black. The particle inside the gun is bombarded by thousands of incident waves, one from each point on the target screen, and the particle makes a random choice as to which wave to respond to. Once that choice is made, it has an impact on that particular incident elementary wave. It triggers from inside the wave the emergence of a Schrodinger wave packet, which then carries the particle backwards out of the gun through one of the slits, it doesn't matter which slit, and inevitably, with a probability of 1, a dot will appear at point alpha on the target screen. After the particle leaves the gun, it has a trajectory, namely that the Schrodinger wave packet will follow backwards the elementary wave trajectory from which it arose. So as you can see in this model, every particle is located in only one place, not two. It is easy to prove that this model produces the same pattern as you expect on the double slit final data. Our model can explain complementarity. In order to know which slit a particle used, you have to put a small light and detector inside the experiment, and the energy of that light is infinitely more than the energy of the elementary waves passing nearby. The light energy destroys the superposition additivity of the elementary waves going through slit A versus slit B. And therefore, when those two elementary waves, slit A and slit B, converge on the particle gun, they have no superposition additivity. They are like strangers. They don't recognize each other. There is no longer any wave interference, and therefore when you look at the final data set, the data tells you you have destroyed the wave interference at the gun. In summary, with this new mathematics of the Schrodinger wave packet, in which we consider the wave packet in the larger context of an elementary wave traveling in the opposite direction, experiments change their meaning. Experiments that used to say that time can go backwards in the quantum world no longer say that. Experiments that used to say that a particle can be in two places simultaneously no longer say that. Quantum weirdness is gone.